Hello dear students, welcome back to my channel. So as you know that uh, we completed two lectures in EMI. Today we will be discussing lecture number 3, right? So let me check. Jasif, Walaikum Salam beta. Hasana, hello beta. Am I audible? Yeah. So I am audible as well as visible to all of you. So 1 second. Okay. And today the connectivity is also good, right? So let's start the lecture now. Okay. So as you know that we started EMI, then so let us recall some previous topics, right? So we just concluded many topics. That is, we can just magnetic flux, right? So in the last class we discussed magnetic flux. What? Okay. Thank you, Beta Jasif. So we just completed magnetic flux. Okay, how the magnetic flux will be maximum when it will be zero, and how to get its equation, right, for any kind of angles, and some properties of magnetic flux, and for 2D figure or for 3D figure, how we can do this calculational thing. Okay, and what is the area vector thing, and how to get the direction of area vector, and these things I guess we concluded in the last class. Okay, so, and Faraday's law of EMI, then how the induced EMF will get produced. So it is only if we just change the flux from any surface, and flux we can change. Now, look here, flux we can change by if we change the area, or if we change the speed, or if we change the magnetic field. So then, okay. So in today's lecture, we will start Lenz's law. Okay. So we will start Lenz's law. Okay. So from I can write here. I can write here. We know what is flux, right? What is magnetic flux? We know it. Done. Okay. That means how many number of lines of electric force, magnetic forces cross your area. Okay. That is your flux denoted by phi, and it is B dot A. B dot A. Okay. Then we discussed Faraday's law. Faraday's law of EMI. Okay. It stated that if we change flux, so it stated that change flux is responsible to get our induced EMI. Induced means the affected one. Induced EMF. Then, but we don't know now. Look, I know that from induced EMF we have induced current. We have induced current, but current is having direction. Now we don't know the direction of the induced current. So to get the direction of induced current, we are having second law known as Lenz's law. Lenz's law. So Lenz's law gives the direction of your induced current. Lenz's law gives the direction of induced current. So and the statement for the Lenz's law is, I can write here for the Lenz's law. Okay, Lenz's law. And the statement of Lenz's law is like the direction of induced EMF or your induced current is such a way that it will oppose the very first cause, the very first cause by virtue of which it has been produced. That means the direction of your induced EMF or the induced current, it will in such a way that it will oppose the cause which created these things. Okay, sir, how we can just get it is better understanding? Suppose, look now, we are having some numericals. Okay, from this numerical you will get the idea. First numerical. First numerical is, look here, find direction of, you can find direction of induced current for given cases. Okay, how to get it? Look now, if this is my wire, yes sir, and current is flowing through it, this is I now. In my wire current is flowing and this current is increasing. Now you can see it is increasing. My current is increasing with respect to time. That means current is not constant, it is increasing. 2 ampere, 3 ampere, 4 ampere, 5 ampere, 6 ampere, it is increasing. Okay, look now. Now, if the current is flowing through this wire and it is increasing, what will be the magnetic field around this wire? Take your right hand, take your thumb in the direction of current, stretch your fingers where you need to find the magnetic field. So we know that, sir, this side the magnetic field will be inwards and this side it will be outwards. Dot, right? Now current is increasing, it is changing. I guess if current is changing, my magnetic field is also increasing. If my magnetic field is varying, so what is phi? Sir, phi equals to B dot A. If my B is increasing, so you can write flux is also increasing. Flux increasing. Flux increasing. Now let us use now which law? Now we can use Lenz's law. Lenz's law stated that my induced current, or EMF, it will oppose the cause. So I guess here the cause is flux is increasing. Flux is increasing. Or my magnetic field is increasing. So in this loop, current will flow in that direction which will oppose the flux increasing. If this is inverse, so if I need to decrease the value of this particular thing, so I need to get my magnetic field in the opposite direction. That means I need my magnetic field outwards. This outward magnetic field will decrease its effect. Now if my magnetic field is outwards, so what will be the possible direction of my current? Take your right hand, take your thumb here, no? Is it outwards? Okay, so it will be anti-clockwise. So my current will flow in this. This is my flow of my current. It's my induced current. This is Lenz's law. So look, the cause of this current is this magnetic field. So this current will oppose its cause. Cause is inward, so it is, this thing is, it needs to be outward so that it will decrease it. It will oppose it. If let's suppose, look now, B is increasing. So according to the Lenz's law, it will try to decrease it. If magnetic field is decreasing, so Lenz's law try to increase it. Look now, this one, look now, this one. Here, my current is constant, it is fixed. But you can see this loop is getting away from it. If it is getting away, so I guess my magnetic field is decreasing. It is decreasing. Okay, it is going away, so it is decreasing. So according to the Lenz's law, if it is getting decreased, it is decreasing, right? So the current will flow in this loop in such a way that it will increase it. How, sir? I guess if current will flow in this direction, if current will flow clockwise direction, okay, so what will happen now? You can see this current magnetic field will be also inverse. Both are in same direction, so it will increase. Look, initially magnetic field is decreasing, but current flow in such a way that it increases the net magnetic field. This is the statement of your Lenz's law. Clear? Clear, or is there any issue with this particular topic? You can just let me know, no? Okay, I don't have any problem with it. Now do let's question number second. So look, what do we need to find out? A current flows from A to B. Done. My A, my B. A, B. A, B. The direction of the induced current in the loop is, first of all, for induced current, we know one thing, that my flux should get changed. No? If there is a change in flux, so I will get my induced EMF, then induced current. How, sir? Because E equals to d phi by dt. Done. Look now, current is increasing. If this current is increasing, you can take right hand thumb in the direction of current, you will get your magnetic field here. It is outwards, dot, and it is increasing. Current increasing, it should be also increasing. If it is increasing, so flux which is associated with it, that should also increase, no? Increasing. So we know one thing, that according to the Lenz's law, the current will flow in this loop in such a way that it should oppose the increment of the magnetic field. If this magnetic field is inwards, so in the loop it should be what? If it is outwards, it should be inwards. Yes, sir, inwards. Inwards means clockwise direction. How, sir? Take your fingers, no? You will get your B inwards. So look, this one is inwards, outwards. So what will be the net effect? Sir, increasing, it will be now decreasing. Decreasing. So if it is increasing, my nu will try to decrease it. If it is decreasing, my nu will try to increase it. Simple. Now look, in this case, look now. My current is decreasing. I know that B is outwards. I know it very well. But if current is decreasing, that means B is also decreasing. This thing represents decreasing. If this is decreasing, so flux which is associated with it, that is also decreasing. So my current will flow in this loop in such a way that it will oppose it. What is the opposition of decreasing? Increasing. So how to get the increment of it? The magnetic field will be in the same direction. So you can take your right hand and you will get that my current should flow in the anti-clockwise manner. So you can take your right hand, anti-clockwise manner, my B will be outwards. Both outwards, that will try to increase this thing according to the Lenz's law. Now third one. What is third one? 1 second, Beta. Okay, this one now. This one. Okay. Look here, my current is constant. If current is constant, I guess my flux is not changing. You can say it is not changing. If flux is not changing, so what should be your answer? Sir, my induced current through this loop will be 0. One case is increasing, one is decreasing, and one is constant. I guess you are very clear with this topic now. Some more numericals so that you will have a very good response on it, no? Look now, look now, look now, look now. Look here. A conducting loop is moving from left to right through a region of magnetic field B. Its four positions are shown below. Show the direction of induced current in all four positions. Done. Look here. If we talk about position 1, in position 1, B is 0. If B is 0, the flux will be 0. If flux is 0, the current is 0. Done first case. Now second case, it is going inside. So I can write B is increasing. If B is increasing, so flux is increasing. If flux is increasing, so the induced one will be in such a way that it will decrease its effect. It will decrease its effect. So how it should look like now? Huh? So it will looks like in this way, anti-clockwise, because anti-clockwise means it is B dot, dot means outwards, inwards, outwards, opposition, decrease, increase and decrease. No? Now third, it is full. This loop is full inwards. So what is phi? Is it BA cos theta? Yes, sir. No change in angle. No change in B. No change in A. Flux is constant. If flux is constant, so what you will write? You will write no induced current. No induced current. Here I equals to 0. Now look, it is going outwards. It is going now. It is leaving the magnetic field. So you will write, sir, B is decreasing. If B is decreasing, so flux is decreasing. So Lenz's law states that it will oppose its cause. Opposition of the cause is increase. It is decreasing, so it will try to increase it. Increasing time means it will be in the clockwise manner. Right? It will be clockwise manner. Why? Because clockwise is also cross, na? Inwards. Inwards, it will be increasement. Na? Here is decreasing, it will be increment. Now, question number next now. An aluminum ring B faces an electromagnetic A. The current I through A can be altered. So this one, now it can be altered. Then which of the following statements is correct? If I is increases, A will repel B. Look now, if current is going inwards, so you can write the flux will be going in this way by your right hand. No? If flux is going now, we know that north pole is leaving, south pole is entering. We know it very well. Now, if my this thing is increasing, if my this is increasing, now look, it is going in this way now. If it is increasing, so here through this loop, it will try to decrease it. Decrease. How decrease? It will go opposite to it. It will go opposite to it like this now. It will try to go opposite to it in this way. Okay. So now this thing is leaving. You can see now. Look here. So it will try to oppose it. Oppose means it will go opposite to that direction. No? Leaving means north pole. This is south pole. Look, south. What will happen now? Repulsion. So if I decreases, A will repel B. No. If it is decreasing now, if it is decreasing, so it will be in the same direction that it will attract it. If I increases or decreases, B will not force any force. No, wrong. If I increases, A will repel B. A will repel B. Yes. C option is correct. C is correct now. Next question now. Look. What is the direction of induced current in resistor R? Look now. Magnetic material is going in this direction. So in this loop, current will flow that should oppose it. No? So north pole will oppose it. Here will be only north pole. If my flux, it will go in this way. North pole, it will be south pole. Done? And you should know with this particular formula. Huh? So my current will go in this way. It will go in this way, and look now. So current will flow in this direction. Easy or super easy? Easy or super easy? Next question. Look now. What will be the direction of current in the loop A as the switch S is closed? You can see here my S is not closed. If S is not closed, loop is not closed, so no current will flow. Now if we close this switch, now positive side, negative side, my current will flow in this direction. My current will flow in this direction. Done? Look now. Firstly, at t equals to 0, current is 0. At t equals to t, current is, let us suppose, 4 ampere. You can see, look now. Current goes from 0 ampere to 4 ampere. That means current increases. If current increases, that simply indicates B increases. If B increases, that simply indicates phi increases. If phi increases, so we know that Lenz's law, it should be opposite to it. Now, with respect to this current, my magnetic field will be outwards, no? My magnetic field will be outwards, and it is increasing. So the current we should flow in the inverse, no? It should be in that direction, that it should oppose this one. So I guess that is only possible if it is going in clockwise manner. How, sir? If clockwise manner, B will be like this. Now you can see now, dot cross opposite to each other. So it is clockwise, not clockwise. Option A is correct. Option A is correct, no? Done? Look now. After, if now we know that now, sir, it is maximum value. After a maximum value, my current will be constant. If my current is constant, so I will be 0. Induced one. Next numerical. See now this one. A bar magnet, you can see now, a bar magnet is dropped through a horizontal aluminum ring along the axis of the ring. What will be the direction of induced current in the loop for the observer shown? What will be the direction of magnetic force experienced by the bar magnet? Look now, if my bar magnet is going downwards, so what will happen now? My flux will increase. If my flux increases, so according to the Lenz's law, through this loop, current will flow in that direction that will oppose this increment. So north, so this will get a north pole. North means anti-clockwise current. Okay. Now, north repels. Repel means Lenz's law. Look now. My magnet is going downwards with the acceleration g. But what happens now? Due to this north repulsion, there is a force of repulsion, F repulsion. F repulsion. So what will happen now? Sir, your magnet will go downwards with some acceleration A, but that acceleration will be less than acceleration due to gravity. Why? Because there is a force of repulsion. Easy? Easy? If now, let us make this numerical different now. Let us, we are having a loop, but it is not completed in this way. North pole, south pole. What will be the acceleration of it? Sir, if this loop is broken, so there will be no induction thing, no? So my acceleration would be G. No force. Now this one, look now. Different numerical. Electron beam accelerated. If electron is going from left to right, current will be going from right to left. We know it very well. Now electron is going from left to right, but due to which current will flow in this direction, I. So if it is going in this way, so my B will be inside. If it is inside, so Lenz's law will try to oppose it. It is accelerated, that means it is increasing. Increasing means it should be dot. What is dot now? Anti-clockwise. Anti-clockwise. Easy, no? These are very easy things. Very, no, extremely easy things. Done? Okay, now electron positive, positron. It is going in this way. Positive is going in this way, now. So the current will go in also this direction. It is retarded. Retarded means decreasing. So you can see now, B is outwards, but it is decreasing. Lenz's law try to increase it. Increases. How, sir? So my B should be also in this direction. That means current will be anti-clockwise manner. Current should be also in anti-clockwise manner. Anti-clockwise. Why, sir? Because now B is outwards, both will be increasing now. This numerical now you can see here. Sir, alpha particle, no issue, uniform motion, V is constant. V constant, so phi is not changing. Phi is not changing. If phi is not changing, so you can write I induced equals to 0. Okay, next numerical. A good concept, now you can write here important concept. That is, a conducting wire frame is placed in a magnetic field which is directed into the paper. Done. That means inside. Na? That means B cross. Okay. Now, the magnetic field is increasing at a constant rate. That means this B is increasing. No? Then, the direction of the induced current in the wire AB and CD are. Okay. If you are having two loops, consider big only. Consider big only. Then the smaller one is a byproduct of that. Don't use Lenz's law on the smaller loop. Don't use the Lenz's law. How, sir? Look now. You will get confused. Look now. If B is increasing, you can see if B is increasing. That simply indicates that, sir, B is increasing, so flux is increasing. Flux is the cause of current. So the magnetic field will in such a direction that it will oppose this cause. Sir, how it will oppose now? You can see now. If a current will flow in this direction, so the magnetic field will be outwards. This outward and this is inwards. Both are opposite. It will decrease. Initially, it was increasing, no? But Lenz's law tried to decrease it. How it will decrease? So look, initially it is inwards. Now we are getting it outwards. Inward, outwards, minus. So now this current is flowing like this. So it will go in the same direction. Don't use Lenz's law, no? Why? Because if you lose Lenz's law in this page, you will get confused. Don't use it. Done? Don't use it. So now current flows from D to C. Look, this option is wrong. Now let's talk about these options. D to C. Now here D to C, then here is B to A. Option number A is correct. A good numerical. Look now, let's talk about this one now. Look, magnetic field, that is B. It is inside and it is increasing. If it is increasing, according to Lenz's law, my current should flow in the loop in that particular direction, that it should be decreasing the effect of B. So if B is inwards, so my induced things will be outwards. So our aim is to get my B outwards. So to get the B outwards, how should the flow of charge, no? current, it will be like this now. It should in this way now. Is it anti-clockwise? Yes, sir, it is anti-clockwise. Now, if we talk about this loop, you will get confused now, no? Look here. Look, B is inwards and B is increasing. So we know that, sir, B should be outwards. So it should like go in this way now. It should go in this way now. Look. In this loop, it is anti-clockwise, but this loop is clockwise. But consider only this one. My answer is anti-clockwise only. My one is anti-clockwise only. Okay, this one now. Look, this one is big loop. This one is big loop. So we need to consider only this big loop. If B is inwards and B is increasing, so here my B should be outward, that it should be anti-clockwise. It should be anti-clockwise. But internal one, it will be clockwise. Don't consider the inner one. Nah? So my answer is what? Anti-clockwise. Look, why I am not explaining why anti-clockwise direction of it, because we know now. I just gave you all this information in the back chapter now. It is not a good decision now that in every chapter I will give the basics of that now, because in previous one I just clear all these things now. Cross means inward, dot outwards. If the direction of current is in this way, what will be the direction of magnetic field? Biot-Savart law. Okay. So all these magnetic chapters are interrelated. Don't miss anyone. Okay, this concept, this is related with what? KCL. Okay, look now, how it is related. Look now. B is inverse, B is increasing. So outer loop, take only this outer loop. It is big. So my magnetic field should be outwards. That means this one. If I current is flowing, I. Now what will be the current in this one? What will be? Look beta, we know that if I current is leaving, I should entering. So in this loop, I current is 0. Then what about this one? Similarly, if B is inverse, so this in this one also current will flow in this particular manner. So in this connecting wire, no current will flow. So my answer for this one is anti-clockwise. For the inner one, it is also anti-clockwise. Look, every numerical, I am just giving you some different concept of thinking, right? Every numerical, I am giving a different concept. Find direction of induced current in the given case. Okay, no issue. So we are looking from this particular angle. So if current is like this, so you can see it is anti-clockwise current. Anti-clockwise. And this loop is going away from it. If it is going away, so B is decreasing, phi is decreasing. So current will flow in such a way that it should be attracting it. Look now, anti-clockwise means this is north face. If this is north face, so this face is south face. If this is south, so it should attract it. Now it would be north face and south face. So my current will be anti-clockwise. Simple. My current will be anti-clockwise. Simple, no? Easy or super easy? Huh? Easy or super easy? Look, let's think about this one now. Look, this one is at rest. Source current is increasing. So look, it is anti-clockwise. Now anti-clockwise means this is north pole, this is south one. This current is increasing. So in this one, my current will flow in such a way that it should decrease its effect. It should decrease its effect. How it will be now? Look now. So my loop will be like this. So if you need to decrease effective, so I need to get my field, it is outside, outwards. No? Look, this one is in this way, this one is in this way, it will decrease it. So that means this is south face, this will be north face. Easy. Easy now. These are super easy things, right? So look, if you can see now, every numerical, I have given a different concept of thinking. If something is falling, if loop, we are having two loops. If we are having this numerical of observation, how we can deal with it? Okay, now this one. In this one, we are having capacitor. We are having capacitor. So if this is my capacitor, positive one, so here I have a positive. Negative, so I have a negative here. So here I need to find out on what plate we are having positive and we are having negative charge. Look here, north pole is there, south pole is there. So the magnetic field will be in this way, now. You can see now the south pole is getting closer to closer. So that means B is flux is increasing. So according to Lenz's law, it should decrease it, no? Decrease it. So what will be the decrement? Sir, it will be in this way. It will be in this way. Done. So if it is in this way, so I guess this is south pole now. This will be north pole. South pole means clockwise direction now. So my current will that will flow in this loop now. That will be how much? Clockwise. Clockwise means in this way. In this way. So look, if current will flow in this way, so direction of current means positive. So this one will be positive now. This is negative. So A is positive, B is a negative. Okay, next one. Next one. You can see now, look, a proton is moving along x-axis as shown in the figure. The direction of induced current in the loop is, see now, my proton is approaching the loop. My proton is approaching. That means my B is increasing. My B is increasing. So it should decrease it. Decrease means, and it is now, look, if proton means positive, that means current is going in this way. So B is in this way and it is increasing. So my flux should be decreasing it. Decreasing means clockwise. Sorry, clockwise. Okay? No. My answer is anti-clockwise. You know why? Sir, if we are having anti-clockwise, that anti-clockwise will give my magnetic field outward. Inverse outward, that means a reduction of the charge. Look, first anti-clockwise, no? First clockwise. This is correct. Clockwise only. We don't know, no? Look. Now, when my current, this proton is here, now, it is maximum. Then it will go in this way. So now, if it is leaving, So B is inverse, now. But it is leaving. Leaving means decreasing. If it is decreasing, so my Lenz's law is stating that my current will flow in such a manner that it should increase this. Increase means it should be inverse. Inverse means anti-clockwise. That means B option is correct. My B option is correct. Okay. Question number, next one. Okay, now question is, an electron moves on a straight line path xy as shown. Done. This is path. Okay. The ABCD is a coil adjacent to the path to the electron. It is electron. Electron means if electron is going in this way, so my current will flow in this way. Okay. And B will be inverse, right? It will be inverse. No issue. So here now look. No, here. One second. No. One second. Look here. So it is not like this. My answer is correct, but look, current is here. So B will be dot, B will be cross, B will be dot, B will be dot. Answer is correct. First clockwise, then anti-clockwise. Okay. Look now. If my current is going in this way and here, na, so it is decreasing. Firstly, it should be increasing, then decreasing. No, wrong. A, B, C, D, A, B, C, D. No, it is not constant. No, answer only this one. The current will reverse its direction as the electron goes past the coil. Yes. Look, if the electron is going up to this particular point, it will behave differently. When it is just crossing the coil, it will behave differently. No? Why? Look here. If the electron is approaching, current increases. If electron is leaving, current decreases. So the magnetic field which is associated with the current, that should also fluctuate. That means induced current will be there and direction will get changed now after crossing it. So answer number D. This one now. So okay, look now. Just you can see here a ring B is placed coaxially with solenoid A as shown as the switch S is closed at okay, no issue. Look, when we close it, current should flow from this one now. Okay, if it should flow, it will flow. Okay, so this will be a north pole, south pole. Done. So look now, what will happen now? What will happen now? Now, my current at t equals to 0, I is 0. At t equals to t, I equals to let's say 4 ampere. So in this change, I guess current is increasing. Current is increasing, that means B is increasing. If B is increasing, so my induced current will flow in such a way that it should decrease. Now look, this one flux is in this way, so there will be an opposite of it. Why? Direction opposite means decreasing. It is increasing. Lenz's law stated it should be decreasing. A is repelled by A. Why? South and this is south now. South, south, repel. Now this one now. A conducting ring is placed around the core of an electromagnet as shown in the figure. When K is closed, it is closed, so current will flow in this loop in such a way. So it will go like this. B, North Pole, South Pole. And it is increasing. If it is increasing, so it should decrease it now. South, South, North. C option. Okay. So I guess now we have done enough things, right? We have done enough things. One second. Easy beta? Easy or super easy? Let me check your response firstly. Okay, look now. Let us start topic known as self-induction. Self-induction. I will take only 5 to 10 minutes, then we can just stop the lecture. Self-induction. What is self-induction? Look now, if this is my coil, you can see now this is my coil. Or you can write inductor. Look now. Let us suppose we just close it. When t equals to 0, that means when my key is open, I is 0. When t equals to t, closed, when my key is closed, so I will be also 6 ampere. Maximum current, right? Okay. So look, firstly, my current is 0. Second time, it is 6 ampere. From 0 to 6, I guess I is not constant. It is changing now. How, sir? Look, 0 ampere, 1 ampere, 2, 3, 4, 5, 6. Yeah, it is a fraction of seconds. Huh? It will take, let's suppose, a fraction of second. Fraction of second. So in this particular fraction of second, now what will happen now? I is changing. If I is changing, the magnetic field which is associated with I, that is changing. If that is changing, flux is changing. So there will be a repulsion. Lenz's law. That means current is flowing in this particular way. Positive, negative. Now, look now. Current will go in this way. 1 second. In this way now, current I flowing like this, going up in this way. Done. So this is my north pole. This is my south pole. So my magnetic field, it will go in this way. Now what will happen now? Sir, I is not constant for fraction of second. It is Srinidhi. No, but I am not teaching offline anywhere, right? I am teaching online only. I am with some institute, no, but taking only the online classes, not offline. Look now, if I is not constant, look, this process is only for fractions of seconds. Okay, for fractions of seconds only. Now you can see now, sir, current is flowing through it. Okay, no issue. And here we are getting my north pole and south pole. Done. So through this, if I is increasing, so phi is increasing. So Lenz's law stated that there should be a current which should oppose it. That simply indicates that if current is going in this way, so I induced should be in this way. I induced. It is I induced. Okay, that means the flux which is changing in this loop, it is proportional to the current. Long current change, long flux. More change in current, more flux. So look, here is a proportionality sign. Now, so if we can write phi is equals to a constant known as L, then we are having same thing, that is I. What is this I? This I is known as coefficient of, this means coefficient of self-induction. Coefficient of self-induction. Easy? Look, initially current is flowing from left to right. We know it, and it should continue flowing from left to right. But due to that current which is flowing from left to right, no, we are getting an inductional thing. We are getting a Lenz's law thing. That postulate is that state is that if there is a flux change, that flux will give rise to the potential difference, induced EMF. And if there is an induced EMF, or simply if there is a potential difference, there will be a current also. But the direction of current, that will in that particular direction, that it should oppose its cause. What is the cause? Sir, cause is this current. That's why it is opposite to it. Done? Any confusion now? Any confusion, beta? Any confusion now? I guess we are done with today's class. So we will continue the session now tomorrow, same timing, right? 10:30 every day. So okay. So I guess we need to stop now the lecture. Okay. If you want anything from my end, if you want any support, now, so what do you need to do? Just go to my Telegram channel. That the description part I have given the channel name in the description part of my channel. So you can just go and just log in. Okay. So I guess we are done with today's lecture. So if you find any difficulty, just reach out to me. And beta, good night. Take care. Bye. Good night. Thank you, beta. Bye. Good night.